All right, so this is from the 2003 AP exam. So what we have is a railgun. It's a device that will accelerate this bar with the use of a magnetic field. So a couple things that I want to mention in the problem before we start. So it tells us right here that the rails are frictionless. We don't have to worry about friction. There's this bar that is riding on these metal rails, and that bar completes a circuit. If you look here, there's a circuit, right? So we got a battery, there's positive, there's negative. So we have current that's going to be cruising out of the battery. The current comes out of the battery, goes this way, right? Then it reaches this bar. The bar completes the circuit, so the current goes up like that and then back around again. Okay? What else? Let's see. Oh, they also tell us that between the rails, they mention right here, there's a uniform magnetic field that's perpendicular to the plane of the page. So what does perpendicular to the plane of the page mean? It means the magnetic field is either going to be going into the page or out of the page, directly in or directly out. In fact, you know what? This is what they're asking for in part D right here. In part D, it says, in what direction must the magnetic field point in order to create a force to the right? So how can we figure out which way the magnetic field must be? We're going to use right-hand rule number 1 or number 2? Number 1. Number 1, right-hand rule is your thumb is the charge motion, which is taken to be positive charge motion. Remember, everything in physics is based on positive charges. So see this current right here? The current flowing through the bar? Is the current in the bar, is that taken to be positive charge motion or negative charge motion? Positive. So right-hand rule says your thumb is positive charge motion, your 4 fingers are the magnetic field, and the palm of your hand is the force. So if you're watching this video at home, you can't really see what I'm doing. But basically, if you're here in the room, right? Basically what you do is you put your hand like that, your thumb points in the direction of the current, your palm has to be the force. So which way are my 4 fingers? Into the screen or out of the screen? Out of the screen. So you answer part D with right-hand rule number 1. So the magnetic field that's between these rails, we could put a bunch of dots in here. So these dots represent magnetic field coming directly out of the screen or out of the paper. So we'll label that with B. B out. Okay, so first question. Determine the position X of the projectile, which is this bar. The bar is the projectile. As a function of time. So look at, what does this mean? As a function of time. Shh. That means that T is going to be in our answer. Oh, and also, look, A, B, and C, I know kids hate this. Kids prefer numbers. A, B, and C are all variables. You know, your answer is going to be non-numeric. So here's how you do it. So they want the answer in terms of, so it says up here that we're allowed to use F, other quantities given, and then fundamental constants. So here's what you do. If you look at this bar, what's the only force accelerating it? If you sum the forces on that bar in this X direction right here, in the X direction, what's the only force on the bar in the X direction? It's F, right? It's the force of the magnetic field. What is the sum of the forces always equal? MA. So A must be equal to F over M. Okay, determine the position X as a function of time. So now what we do is we go to a kinematic. We go X equals 1/2 AT squared plus V initial T. It tells us right here that it starts from rest. So V initial is 0. So we take A. Hey guys, stop talking. So X is going to be, so you plug that in there, it's going to be 1/2 F over M t squared. And then we'll clean that up for the answer. So this is going to be ft squared over 2m. Bam. That's the answer. You really didn't even need to know about magnetic fields to do that, right? This was basically, all right, F equals ma, find what A is, plug that into a kinematic. Okay, any questions with A, with this one? Okay, B. Okay, part B. Determine the speed of the projectile as it leaves the right-hand end of the track. Now, I'll be honest with you. The first time I solved this, guess what I did? I kept T in my answer. I would have gotten points off. I wouldn't have gotten to 0, but look, A allows for T, right? It says right here, as a function of time, you can use T. Are we allowed to use T for part B? Because it's not one of the givens up here, right? You can't use T. So what we do for part B is we go to another kinematic. So again, you don't even need to know magnetic fields at all to do this. Vf squared equals V initial squared plus 2ax. That's one of the motion equations. V initial is 0, so V final is going to be square root 2ax. But dude, what is this x? What is the x there? L. It's this. So it's going to be 2al, but we're not done, because is A mentioned up here? No. So what do we plug in for A? What was A? A was, oh, come on, dudes, F over M. Right, so we'll clean this up, make it look super nice. This is going to be 2FL over M, square root. Okay, part C. Determine the energy supplied to the projectile by the railgun. This is actually chapter 5. This is chapter 5, which was energy, work and energy. Look at, guys, what energy does the bar start with? What's the energy that the bar starts with? Nothing. 0. Is it moving? Is there kinetic? No. Is there potential? No. So we start with no energy. Then the bar goes like this. It goes faster, 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 faster. When the bar reaches the end over here, what type of energy does the bar have? What type of energy did the bar gain? Kinetic, and that's the answer. Basically, the energy that it was given, it's in the form of kinetic, so it's 1/2 mv squared. And guess what? Can we just leave it like that? No. I mean, if you did, you'd get some partial credit. But why can we not leave it like this? Is V allowed? No. So what can we plug in for V? Well, we already have V. We did it in part B. V was equal to square root 2FL over M. So just plug that in. So you go 1/2 M square root 2FL over M squared. What happens if you square a square root? It cancels, so this is going to be 2FL over M. The M cancels, the 2 cancels, and that's FL. Now look, why is that no surprise that it's FL? Because what would F times L be? The work. And the work done equals the energy gained, right? The work equation is force times distance. So the answer comes out as FL. All right, last question. Now what we do is we actually do it with numbers. So they give us numbers in part E. So here's what I would do. First, find out what the force is. Hey, force equals what on a bar? B, I, L. But look, do we mean this L? What distance should we be using for the force on the bar? This distance. So you got to change this to BID. This is the equation for a force on a wire in a magnetic field. Okay, so what's the force? So B is 5 Tesla. The current is 200 amps. D is 10 centimeters, which you got to put in meters. So the force comes out as 100 newtons. Okay, so then what is A? A was what? F over M. So that's 100 newtons over 0.5 kilograms. So hey guys, give me 20 seconds, 20 seconds. That's 200 meter per second squared. And then plug that into a kinematic. So then you go VF squared equals V initial squared plus 2AX. This X is actually L. So this is going to be VF 2AL. L is 10. So this comes out as 63.